My name is Joe, and I have to start by apologizing in advance. There's not much separating me from the road, and we often get emergency vehicles at this time, so there might be sirens all of a sudden. Yeah, today I'm going to tell you about two plethories, which is coming from my paper with John Baez and Todd Trimble called Schur functors and categorified plethism. So I'm not going to tell you about Schur functors today, but I'll tell you about categorified plethism. And I'm going to start the talk sort of backwards and tell you our main theorem immediately without explaining what all these mean. So the main theorem is that the two plethory structure on rep fin S induces the plethory structure on K of rep fin S, which is the same as lambda. So if you see this, I'm guessing that you have maybe 2 to 5 questions immediately, which are these, I think. So what is K? What's a plethory? What is rep fin S? What's lambda? And what's a two plethory? So basically the rest of my talk is going to be just answering these questions so that you can understand what this theorem is saying. So I'll answer the first question immediately. Say K is the Grothendieck ring. It's the same thing as the Grothendieck group if you haven't heard of the Grothendieck ring, but you have heard of the Grothendieck group, but just in the case where you also get a ring structure. And I won't go into more detail about that than to say that you take isomorphism classes, and then that gives you a semi-ring or a rig, and then you group complete it. And that's what K means. But now the next question, what is a plethory? So before I can tell you what a plethory is, I have to tell you what a biring is. And before that, I have to tell you that by ring, I mean a commutative and unital ring, kind that algebraic geometers tend to care about. So now I can tell you that a biring is a ring object in ring op. You need a Cartesian monodal structure to define a ring object internal to a category, and the tensor product happens to be the co-product in the category of rings, and so it's the product in the category of rings op. So that's exactly what we need to define this. And we define the category of birings to be ring and ring op, and that's just to make sure that the morphisms between these are ring homomorphisms and not backwards ring homomorphisms. An equivalent way to look at this definition is to say that it's a ring which is equipped with a bunch of ring homomorphisms to give it extra structure that look exactly like the ring, all the structures of a ring, but backwards. So we have a co-addition and a co-multiplication and a co-negation. And these are all associative and unital and distributive in the dual sense. And here's some examples too. These are going to be examples that I carry through the rest of the talk, or like analogs of these come up later. So we have Z, it's the initial ring. It's the free, so another way of saying that is that it's the free ring on 0, on no generators. And it has a pretty boring biring structure. But the second example is also free. It's the free ring on 1 generator, and it has a more interesting biring structure. So I have all the formulas written out here. You can look at them. I won't say them out loud. But I want you to notice that the way that I define all of these, the way that I'm defining them here, depends heavily on the fact that this is the free ring on 1 generator, because I'm only telling you what it does to the generator, and then you know, you can infer the rest it's induced by that. I just want you to hold on to that piece of information. It's important. But we get these operations as I have them satisfy all the rules to be a dual version of a ring. But what can you do with a biring? You have this kind of structure on your ring. In general, ring, the Hom Hom set between two rings, the set of ring homomorphisms, doesn't get to be a ring with like pointwise operations. You can try it out. If you try to add two ring homomorphisms, it's not going to be a ring homomorphism. But you can, when your biring, when your domain ring is a biring, this can be used to induce a ring structure on the Hom set. And this is how you do it. So you pre-compose with these biring structures. This is the co-addition of B. So first you start by co-adding, and then if you have these two ring homomorphisms, F and G, you do those in parallel, F tensor G. And then you do the co-diagonal for rings, which is multiplication. And that will be a ring homomorphism, because all of these things that we're composing are themselves ring homomorphisms. And multiplication is the same. And so you can put a ring structure on this Hom set. Moreover, this gives you what I'm calling a lift of the representable. So we get this representable functor from B, but it lands in set in general. But when it's a biring specifically, then you can use this ring structure that I've hinted at above to lift this to a functor to rings. I mean, just forgetting the ring structure that you imposed is what it means to compose it with the forgetful functor. So let's look at our examples that I've said we're going to carry around. The functor that Z represents, because it's initial, the set it produces here is always going to be a singleton, and so this is always 0, and so this is the functor that it lifts to is the 0 functor, the one that produces 0 all the time. But polynomials is more interesting. It's free on 1, and so the set of homomorphisms into a random ring R is going to be exactly the underlying set of that ring. And so the functor that lifts this representable is the identity functor on the category of rings. Something that I won't explain at all, but I'll just tell you about is that when you have a functor like this, that's an endo functor on the category of rings, that is a lift of a representable in this way, then it's always a right adjoint. I can hear sirens coming. So it's always a right adjoint, and in particular, we get this equivalence. I'm just going to mute for a little bit. Okay, sorry, they're passed. So we get this, it just gave you more time to absorb this proposition. We have an equivalence between these three categories: the category of birings, the category of right adjoints that you get from lifting the representable, op, and then the category of left adjoints between left adjoint endofunctors on ring, which you think of as being the left adjoints to these lifts. That op is kind of important, just keep it in mind. So now that I've told you what a biring is and I've given you a few examples and what you can do with them, I can tell you what a plethory is. So first of all, if you have two birings, they have these right adjoint lifts, and if you compose two right adjoints, the composite is also a right adjoint. And I told you that birings and right adjoint endofunctors are equivalent, with an op. So that means that because this is a right adjoint, then it must also be a lift of a representable. So there's some other biring which I'm calling B prime O dot B, that this is a lift of its representable. And in particular, that O dot operation that I'm talking about up here is a monoidal structure on the category of Birings. It's not symmetric, but it is coming from, it's essentially coming from saying endofunctors has a monoidal structure coming from composition, and right adjoints are closed under that, so they become a monoidal subcategory, and right adjoints are equivalent to Birings, and so we're just transferring that monoidal structure over to the category of Birings. So we get this monoidal structure on the category of Birings. The unit object is polynomials, because the lift of polynomials is the identity functor on rings. And now I can define a plethory. A plethory is a monoid in this monoidal structure. Another way of seeing what that is to say that it's a bunch of biring homomorphisms. We have one for the multiplication, or the plethism is what it's called. And then there's also a unit element. And so these satisfy the laws of being a monoid. And another way to look at this definition is to say that the lift that you get from it being a biring, since you're taking a monoid with respect to composition, it's also going to be a comonad. That's where the op is coming in. I said for right adjoints, you have to put an op, and so it becomes a comonad. So the lift is a right adjoint comonad, or the left adjoint of that is a left adjoint monad. These are all equivalent things. So first, our two examples, Z is not a plethory. And it comes from really sort of basic facts about rings. So I'll just let you figure it out. Why is the lift of Z not a comonad? But the other one is. So the functor that lifts the representable for polynomials is the identity functor on category of rings, and that's obviously a comonad. And so polynomials gets to be a plethory. And this plethism operation, which I realized I called it P up here and then pi later, is just polynomial composition. So composed two polynomials by substituting in where the x was, that's exactly the plethism operation, making this into a plethory. Great, so we've answered two of the questions now. We know that K is the Grothendieck ring, and a plethory is a monoid in birings with a substitution monoidal structure. And so now I'll tell you what rep fin S is, and lambda. I'll answer both at the same time. So S, by S I mean the symmetric groupoid. Sorry, there's another. Okay, it's done. Okay, so S for me is the symmetric groupoid, and I call it S because it looks like the symmetric groups. You take all the symmetric groups and consider them one object categories and take their coproduct. It's also the free symmetric monoidal category on one. It's also a skeleton of finite sets and bijections. So that's three different ways you can look at it. And we just say that a representation of S is a functor from S into the category of vector spaces. And a representation is finitary if the total dimension of it is finite. So what does a representation look like? It looks like a bunch of vector spaces, one for each natural number, and the corresponding symmetric group always acts on that. So you have a bunch of representations. And the finitary part means that eventually these are all zero, and they're all finite dimensional. And we get a category of these where the natural transformations between these functors are the morphisms. Okay, so for the sake of this talk, for the sake of time, I'm just going to define lambda to be the Grothendieck ring of category. if you happen to know about symmetric functions, this is the ring of symmetric functions. It's a really important thing in algebraic combinatorics and representation theory. But I won't tell you anything about it right now. So that's 4 down. Rep fin S is the category of finite representations of symmetric groupoid. Lambda is its Grothendieck ring. Okay, so last one, two-plethary. What is a two-plethary? It is the title of this talk. So save the best one for last, I guess. Can't get it to go. Oh, okay. So I'm going to tell you what a two-plethary is, and before that, I have to tell you what a two-birig is, and before that, I have to tell you what a two-rig is. So this is going to be our categorification of the notion of ring, and it's going to be a symmetric monoidal Cauchy complete linear category. It's a lot of adjectives, but here's the breakdown of what those mean. Symmetric monoidal category has a tensor and a unit with respect to that tensor. Linear, it's enriched in vector spaces, and for the sake of this talk, I'm taking C to be the base field. And it's also Cauchy complete, which in this case just means that we have biproducts. We have direct sums, and it's products and coproducts coincide. And we also have a zero object. It means it's initial and terminal. And we also have that all idempotent split. And you either know what that means or you don't. If you don't, then you can just ignore it. And we don't have to, so the byproduct gives us our analog of addition, and the tensor gives us our analog of multiplication, but we don't have to ask for distribution because it comes naturally, it comes automatically out of the fact that our byproducts are an example of an absolute colimit. And here's some examples. So these first two examples you should think of as analogs of the two examples of in the decategorified setting that we had before. We have finite dimensional vector spaces is the free two-rig on 0, so that's like Z. And rep fin S is the free two-rig on 1. And then here's a bunch of other ones, but I'm not going to say anything about them. I just want you to know that these two that we have are in good company. So now I can tell you what a biring, our categorification of a biring is. So a two-birig is a two-rig that is equipped with a lift of its representable. So I'm going straight for the lifting the representable thing here. That's like the easier way to go about this. Equipping it with like cooperations you can extract from this, but starting from that perspective is a little tricky. So we're just going to go with this. It is equipped with a lift of its representable. And a two-plethary is going to be a two-birig where its lift is not just a right adjoint, but also a comonad. I just put a 2 in front of all of that. Say it's the two-dimensional version of those things. So our two examples, we have finite dimensional vector spaces. It is the initial two-rig, so it represents the 0 functor. And for the same reason as for Z, it is not a two-plethary, but it is a two-birig. And then again, for free on 1, we have rep fin S, and it represents the identity functor. That's obviously a comonad, so it's a two-plethary. And yeah, so now all the questions are answered, and we can understand the statement of this theorem. We have that we know what rep fin S is. It's a category. It's the free two-rig on 1. So it's a two-plethary. And if you take the Grothendieck ring of that category, you get this thing called lambda, which you may or may not know what it is like, but you know that it exists, as I told you. And it gets to be a plethary, and that's induced by the two-plethary structure. So that's the statement of the theorem. I have nowhere near enough time to like even sketch a proof, but that's it.
Thank you very much, Phil.